Okay, everybody. Good afternoon. Oh, good morning. Once again. Okay, so as usual, I'll get this lecture then. Saeed will be arriving at 12. We're in week 5 now this term, aren't we? So just about nearly finishing the first half of this term. Just to tell you about an update or two on the Moodle area. I put there, it's back a few weeks, it's back in our first teaching week, but I put the solutions to the first tutorial sheet of mine, called the sequences questions. So I put a PDF file there just under the original tutorial sheet. And this is the same tutorial sheet, but with all the solutions. Okay. So you can use that to help you study those topics and to check the work that you've been doing on those sequences questions. And then at the end of my lecture this morning, I'll hand out another tutorial sheet, this time on series. Okay? So we just started the series section, series topic, last week. So I'll be giving you out one of these at the end, and this will get you through the next few weeks' tutorials and the questions on my part. So I'll give you a paper copy today, and there's a PDF copy there in this week's section to refer back to. Okay. So we are looking at series. We introduced these last time. We looked at a couple of interesting examples. Okay. So series is a sum of a sequence. So we're used to thinking about sequences as just lists of numbers, one after the other. This list might have interesting properties in that it might converge to something as the sequence continues, or it might diverge. That's what we've been studying. But a series is when these are added together. Okay? And we have this nice sigma notation using a couple of Greek letter sigma to stand for sum. And this denotes, well, this is an infinite sum because it has the infinity symbol on top. So this is the unending sum of all the elements xi, beginning of 1. And the two key examples we've looked at already, so I'll quickly remind you of these, but we've spent some time discussing these. We had the series of powers of 1/2. So the sum of 1/2 to the power I for every value of I beginning of 1. So this was 1/2 plus 1/4 plus 1/8 and so on. It's easy to visualize and imagine a model of what's happening with this series. You can think of this series as tracking the position of something making steps along the number line. So first you take a step of distance 1/2, then you take a step of distance 1/4, which brings you to 3/4. Then you take a step of distance 1/8, which will take you to 7/8. Then you take a step of distance 16, which will take you here, so on and so forth. We describe that what's happening here is you're taking a series of steps, you're accumulating them all, you're adding them up, so you're stepping one step after the other, making progress along the number line. But at any particular point, if you look at the distance remaining to 1, the next step you take is half of that distance. So you're certainly never going to go beyond 1. You can't go beyond it, because at each stage you only ever step half the remaining distance towards 1. So you're certainly never going beyond 1. But you can also argue fairly well that if you take any point to the left of 1, even a tiny bit to the left of 1, eventually the steps will go past it. So you're going to go past any point to the left of 1, but you're never going to go beyond 1. Therefore, there's really only one sensible value we can attach to the infinite sum, and that's the value of 1 itself. So this is stepping towards 1. Stepping towards and getting arbitrarily close to the value of 1. So we actually write the sum from I equals 1 to infinity, 1 over 2 to the power I. We actually write that it's equal to 1. Now we'll see later on, this is an example of what's known as a geometric series. And so we'll have a nice formula and a nice way of calculating and obtaining the value. But we can kind of argue using more the basic ideas that it should have a value. So this is a convergent series. It's an infinite series that nevertheless has a finite value. So we say it's convergent. A divergent example, these are our first uses of these terms attached to series. A divergent series is, for example, this series here, which is called a harmonic series. It features all the positions 1, 1/2, a third, a quarter, and so on. These are all the positions where you get harmonics in a vibrating string. So there's a nice connection to the sound and so on. So this is the series 1 plus a half plus a third plus a quarter, etc. So you're adding up 1 over I for every value of I from infinity. Now this shares some features with the first example. You're taking a series of steps and you're accumulating them. So you can also track the progress of this series along the number line. First you step distance 1, then you step distance a half, then you step distance a third, quarter, fifth. And superficially it looks like the previous example in that the step size is shrinking and converging to 0. The step size is converging to 0, just like it was up here. The fact that this step size converged to 0 was somehow connected to the fact that this was a convergent series, that it only gave you finite value. So this is still true in this example, but we gave an argument last time. I won't repeat it last time, but you can look up the notes if you weren't here. Last time we showed with a grouping argument partition the terms of this series and demonstrate that you can keep generating halves. Because the third plus a quarter is bigger than a half. The fifth, the sixth, the seventh, and the eighth, when you add them together, are bigger than a half. So last time we showed with the grouping argument that this series increases without upper bound. So although the step size is getting smaller and smaller, just look at the steps you're taking, they're vanishing to nothing. But however, when you add them all up, there's still enough weight there, you're still making progress. And if you care to wait around long enough, or care to take in enough terms into the series, you will see that series get bigger than any value you care to mention. So it doesn't have an upper bound, it keeps increasing without any end. So we say this is divergent. It's not convergent. And sometimes we might write, although there are disadvantages to writing this kind of thing, but sometimes you might see people write this, and it's not unreasonable to write that. The drawback is that it kind of implies infinity as a number, just like the number 1, which it isn't. Be very careful about treating infinity as just a number, like other numbers, but it's not unreasonable to write that kind of thing. But for the moment, you should kind of just understand an equation like that is just a shorthand way of saying that this series increases without any upper bound. It doesn't have a finite value. So those were our 2 examples. So it's important to note that a step size is just a term, is just a phrase I'm using for the term of the series. When we're thinking of the series as we're making positive steps along. It's important to note that a step size converging to 0 is not enough to make the series converge. Okay, because our harmonic series is an example that shows that. Its step size is converging to 0, but yet we saw last time that the harmonic series doesn't converge. Okay. Any questions? Any remaining questions about those 2 examples that are getting us started? So what we're going to do in this chapter is develop a theory about series in a similar kind of fashion to the way we developed the theory about sequences. We want to understand, it seems there's very interesting things going on here. Sometimes we got convergent series, sometimes we don't. So we seek to understand that and to develop tools and techniques that will allow us to detect convergence in certain series and detect divergence in other series. Be able to declare in certain cases whether or not a series converges, whether or not it diverges. And maybe perhaps in some cases come up with formulae that tell you what the sum of the convergent series is. So first, we just pin down the definition of what we're talking about. So this is definition 2.3. And this is our definition of what a convergent series is. And it links the notion of convergence for a series to convergence for a sequence, which we already understand. Okay? So we will say that, I use the same notation. We will say that a series like this converges to L, converges to the sum L, and we'll write that as simply that the sum of the series is equal to L. So we will use this term, converges, and we will write this kind of equation if and only if the limit of a certain sequence is equal to L. So this is how we define convergence for series using the notion of limiting values of a certain sequence. So the sequence we use is the sequence of partial sums. Not the whole series, but just adding up the first k terms. So this object here inside the curly brackets is the kth element of the sequence of partial sums. And if that sequence of partial sums converges to the limit L, That's what we mean by saying that the series converges. So an example of that here with the stepping by powers of a half. So the partial sums are these points that you reach along the way. So half is the first term, 3/4 is a half plus a quarter, so the sum of the first two terms. 7/8 is the sum of the first three terms. So these red points, intermediate points that you meet along the way, those are the partial sums. Those are the elements of this sequence. And we saw, or we appreciated anyway, that that sequence of partial sums converge to one, and so we say then that the series converges. So we see that convergence of series is defined using convergence of sequences. So we will be able to use everything we know, or anything we know about convergence of sequences well, maybe not be able, but we will be encouraged or likely be able to use things we know about convergence of sequences to produce results about convergence of series. Okay. So straight away we're going to jump to one of those, which is Theorem 2.2. Remember, one of the first results we proved about sequences was the Algebra of Limits theorem, which told us, see, using the operations of addition and multiplication, there are a number of obvious ways that if we have two sequences, we can produce a new sequence, either by adding the terms together, two sequences, or by multiplying together corresponding terms of the sequences, or by dividing the terms of one sequence by the terms of another. So you can take simple sequences and manufacture more complicated sequences. And our Algebra of Limits theorem for sequences told us how to relate the convergence of the new sequence to the convergence properties of the ingredient sequences. So we would like to be able to do a similar thing for series, but series are more complicated than sequences. You're adding up the terms rather than just observing a list of terms. So that means that we can't prove any simple results about products of series, maybe, or quotients of series, but we can do it with linear combinations. So that's what's going on in Theorem 2.2. So you've got the whole theorem and proof laid out there. I'll just sketch out the important details and give you some discussion about it here on the page. So it's an if-then statement. So if we've got sum of AM and the sum of BM are convergent series, sometimes we leave off the indexing if we just want to write quickly and it's understood what it should be. So if the sum of AM and the sum of BM are convergent series with, let's say, the sum of AM is equal to this quantity A, and the sum of BM is equal to this quantity B, capital B. So they're both convergent, those series. They sum to finite values. Then, for any pair of scalars or a pair of real numbers, alpha and beta, the new series, so we're taking alpha times AM plus beta times BM. We're going from M equals 1 to infinity. So this is a new series that I've built out of the A series and the B series. This is also convergent. Okay? The new series is also convergent. And it has the obvious sum. I mean, it'd be very strange if this had any value other than alpha times the sum of the first series plus beta times the sum of the second series. So this is what we kind of naturally expect the sum of this series to be. Basically, you're adding all the a's to all the b's, except you're multiplying the a's by alpha, multiplying the b's by beta. So surely you get out of it alpha times the sum of the a's plus beta times the sum of the b's. Now, it's an if-then statement. If all this stuff, then this stuff. So to prove this, we can, the most direct way, the first way you think about proving an if-then statement is to prove it directly. Okay? Where you assume the assumptions, or the conditions. So assume that the sum of AM is equal to A, the sum of BM is equal to B. And then we're going to prove the conclusion, but think carefully about the steps we're using at the things we're using at each step of the argument. The things we have available are the things we have available to produce the proof are the definition of what we mean by convergence for a series. This idea that the sum of this convergent series is the limit of its sequence of partial sums. And in addition, anything we then know about the convergence of sequences, which we've already proved in the weeks up to now. Okay? So we can use that, the definition for what it means for a series to converge, and anything we know about convergent sequences. So this is how we prove it. I take this quantity alpha A plus beta B, and what it is, by definition, what it is it's alpha times, okay, the sum of the A series. But by definition, the sum of the A series is the limit of partial sums of the A series. And by definition, what B is it is the limit as k goes to infinity of the sum up to k of the B series. Okay, that's how quantities capital A and capital B are defined. But here now, I'm looking at alpha times the limit of one sequence plus beta times the limit of another sequence. So using our algebra of limits theorem for sequences, we can say that this is just the limit of the compound sequence, which is alpha times the first element from the sequence, which is the kth partial sum of the AMs, plus beta times the kth element of the second sequence. So this step, from the top line to the second line, that's true by the algebra of limit sequences, by the algebra of limits theorem for sequences. The limit of a linear combination is equal to the linear combination of the individual limits. So the first step was simply justified by the definitions of capital A and capital B. The second step is justified by the algebra of limits theorem for sequences. Now we're looking at the limit of this thing in brackets. But now there's the thing in brackets here, this object inside the large brackets in the middle one. There's no conceptual problems with it. It's just a combination of finite sums. So we can just use very basic algebraic manipulation techniques to express it as a single sum. It's the sum from n equals 1 up to k of alpha times am plus beta times beta. That's not a property of convergence, it's not a property of infinite series or anything sophisticated like that. It's just basic algebra. This is a finite sum here. Might be very long if k is large, but it's still just a finite sum of the same. So this is simply manipulating finite sums. No, nothing beyond high school mathematics or GCSE level mathematics. Okay, just expanding brackets, using the commutativity of addition, reordering sums, and so on. Okay, nothing too fancy. But it does get us very close to the desired conclusion. Now we're looking at the limit as k goes to infinity of what's inside the large brackets now is the kth partial sum of a certain series. Okay? This is adding all the terms up from m equals 1 up to k of this term in brackets. And you're taking the limit as k goes to infinity. So by definition, this is exactly the sum from m equals 1 to infinity of alpha am plus beta beta. So again, that's just by the definition of an infinite sum. And that is exactly what we were trying to prove. We were trying to prove this statement up here. That was the conclusion we were arguing for. So here we have it. The top there to the bottom. Okay? And its equation is all the way down, so the top left-hand side is equal to the bottom right-hand side. Now there is a little comment, if you look in the notes on page 16, there is a little comment in the margins talking about the direction we proved that in. See, the result we were trying to prove was this equation here. Normally, you begin, as we do in English, we read to the left. So our natural instinct would be to start at the left-hand side and develop it through the sequence of equations and get to the right-hand side. I didn't do that here. I started at the right-hand side and developed equations until I got to the left-hand side. It made me a subtle point why I did that. Because if I had started with this if I'd started down here, the left-hand side of the result, I wouldn't have felt comfortable saying that this infinite series was equal to the limit of this sequence of partial sums because I didn't know yet that that limit existed. That was one of the things we were tasked with proving here. We were asked to prove that the series converged. And if this wasn't if we didn't know ahead of time that this was a convergent series, then we shouldn't go talking about its limit because its limit might not exist. Okay? So you have to be careful about talking about things that don't exist because then anything you say about them is nonsense if they don't exist. So I wouldn't have felt comfortable starting here and going that way because I didn't yet know that this limit existed, so I probably shouldn't write it down. Whereas I did feel comfortable coming from here because I knew these numbers capital A and capital B existed because I'd assumed they had. And then by definition they must be the limit of these partial sums because that was the assumptions I made. So I'm on safer ground starting at this side. And then I found that this was a limit of this sequence of partial sums, but I already knew it had a finite value. So I didn't run into any trouble about talking about things that I didn't know existed when we started from this side. can get to the desired conclusion. Yes?
So is it the fact that, like, when you wrote the limit down in the penultimate line, because you knew that that was equal to a finite amount, that sort of authorized you to write the last limit?
I think so, yeah. Yeah, because, I mean, if you start writing the sum of an infinite series, someone might object and say, how do you know it converges? Before you write it down and talk about it. Well, I know it converges because it's equal to this thing, which is a finite value. Yeah. I mean, it's still the same argument whether you run it from the bottom towards the top, or reside it from the top towards the bottom. And you know, if you do start at this side and go this way, although someone could object at this stage, if they allow you to continue the argument, then they discover, well, it is equal to a finite quantity. So in retrospect, you were authorized to say this is the limit of this sequence of partial sums, because we found out a few moments later that it did exist. But maybe stylistically, it's nicer to start on this side because we don't make any of those extra assumptions in the middle of the argument. Okay. Any other comments about that or points to raise? Questions about that? Okay, so that's good. That's our first result about convergence of series. Unfortunately, there aren't such simple results about, say, the infinite series where you're multiplying together corresponding terms. Because there's no way of linking the partial sums of this series to the product of the two partial sums, the partial sum of the A series multiplied by the partial sum of the B series. Or even the series of quotients. Okay? We don't have any such nice and simple arguments to make about these new series like we've done. Okay. So then we move into section 2.5, which is a large section which more or less occupies us for the rest of the chapter, more or less. And this is a whole bunch of convergence tests. So these are tools for judging the convergence or divergence of series. But now there is no one single universal tool that performs perfectly. So there's no simple algorithm or method that if somebody produces a series and puts the series in front of you, that you'll instantly be able to tell whether or not it converges, and if it converges, what the sum is. The situation is it's a lot harder than that. Okay? So there isn't just one magic method or tool that will allow you to judge the convergence status of any particular series. What we have instead are a selection of tools which have partial performance. Okay? So for certain series of a certain type, a certain tool might be able to judge the convergence of that series and tell you, yes, it converges, or no, it diverges. But for any one of these tools, there will be examples of series for which they don't reach a conclusion, for which a certain convergence test, if you try to apply it to a certain series, doesn't give an answer either way. It just says, good, I don't know. So the situation is quite complicated. the concept of convergence for series is complicated and subtle, and there's many different behaviors displayed. So there's no simple kind of universal approach that we might take. But what we have is a whole bunch of partial series. And the first of these is something that we've alluded to when we were discussing our first examples. And this goes by the name of the general term test. Now, what the general term test is, you can think about it as a tool for determining divergence. So the general term test is a basic test that a series must be able to pass in order to have a chance of converging. But if a series fails this test, we can definitely say that it's a divergent series. And there's a couple of ways in which it can be phrased, but so there's two ways it can be phrased. We can say if the limit of the sequence of terms is not zero, then the series of those terms diverges. That's one way of expressing the test. If you're looking at a series, and if you notice that the sequence of terms, just the list of terms in the series, is not converging to zero, then we automatically know immediately that the series diverges. Now, our initial two examples that we looked at, the sum of powers of a half and the harmonic series, they both passed that test because their sequence of terms were convergent to zero. 1 over 2 to the I gets smaller and smaller, converges to zero. 1 over I also gets smaller and smaller, converges to zero. Far slower than 1 over 2 to the I, but they still do converge to zero. So these two examples passed, didn't trigger this test. So to speak. Or an alternative way of expressing the same thing, we can say if a certain series converges, then the limit of the sequence of its terms is equal to zero. So there's two ways of expressing this general term test. What you have to be very careful about is misquoting the test. Okay? As mathematicians, we have to be careful and precise. So there's a link here between the terms converging to zero and the sequence converging, or diverging. But the link goes in a certain direction. If the series converges, then the terms converge to zero, or expressed a different way, if the terms do not converge to zero, then the series diverges. Be careful and guard against misquoting it. It does not say if the step size converges to zero, then the series converges. That's false. I'll say it again a little bit more. So what I'm about to say is false. If the step size converges to zero, then the series converges. That's misquoting this, okay? But it's a common mistake or misstep that people will make when engaging with this the first time. You have to be very careful about making that. Always go back to some of these initial examples. The harmonic series is the classic counterexample to that misquote. The harmonic series, the terms do disappear. The things you're adding up disappear, they converge to zero. But yet, it still diverges. There's still enough weight or mass or accumulation there to make the series grow without any operation. Okay? So there's a direction to the implication. It doesn't go in both ways. Okay? So warning, be careful about misquoting. It can give you a conclusion that the series diverges. It can't give you a conclusion that the series converges. It can give you a conclusion that the terms of the series converge to zero if you know the series converges. But it can never give you a conclusion that the series converges. Okay, so let's have a look at the proof of this. So we're going to prove it by proving the second version statement. Has Saeed introduced you to the term contrapositive of a logical statement?
Yeah.
He has. Okay, so this is an example. These two statements, so when I say are, these two statements are contrapositives of each other. Remember, if the statement is A implies B, its contrapositive is not B implies not A. These two statements are logically equivalent. If one is true, the other is true. If one is false, the other is false. They're logically equivalent statements. So here you have an actual example of it in the wild, so to speak. If the terms do not go to zero, the series does not converge. If the series does converge, then the terms do go to zero. Think about it, you will see that those two are contrapositives of each other. Okay, I don't want to rush. I'll be rushing it a bit too much because I have to hand out the tutorial sheet. So I'm not actually going to go and discuss that. So when I see you tomorrow, I've got the lecture tomorrow. So we'll continue looking at some of these proofs. We'll discuss the proof, the general term test, geometric series test, maybe some of the other ones. And that will prepare you for answering some of these tutorial questions. But the proofs are all in the lecture notes, so feel free to